Photocatalysis is a relatively new frontier in chemistry, but to put it simply, it involves semiconductors behaving as photocatalysts upon the irradiation of their valence electrons by a photon of a particular wavelength. From there, the electrons are excited to reach an orbital of higher energy, while leaving behind a void known as a hole. The formation of electron-hole pairs is crucial, as the excited electrons can facilitate reduction, while the holes can facilitate oxidation, enabling the photocatalyst to produce active species that lower the activation energy required for a particular chemical reaction. What is interesting, however, is that for the same photocatalyst, it is possible for it to catalyze different chemical reactions when they are irradiated with photons of different wavelengths. Fascinating. With that out of the way, let's get on with the interesting Specifically, stuff. The applications of photocatalysis. As you might already know, industrial accidents involving chemicals are not uncommon. They are mostly due to the accidental ignition of volatile compounds during the production process, as heating is required to supply the activation energy of many chemical reactions. Photocatalysis eliminates the requirement of heating within the production process, reducing the risk of the accidental ignition of volatile compounds and saving lives in the process. In addition, photocatalysis can also replace the usage of homogeneous catalysts within certain production processes. This would eliminate the costs involved in separating products from homogeneous catalysts. In addition, multi-phase reaction pathways are also possible using photocatalysts, as the same photocatalyst can catalyze different chemical reactions depending on the wavelength of light irradiating it. What is also worth mentioning is the usage of photocatalysis in the removal of pollutants such as volatile organic compounds. This is done by catalyzing the formation of oxide superanions and hydroxyl radicals, which are extremely effective in breaking down pollutants big and small. The same logic applies for water treatment. However, this feat pales in comparison to the effect of ultraviolet light on certain plastics. More than 80% of the plastic that enters the ocean is broken down by photocatalysis. The most exciting application of photocatalysis thus far is the potential of the photolysis of water, producing life-saving oxygen and hydrogen fuel for astronauts
in the future.
When it comes to photocatalysis, the sky's the limit. After all, photosynthesis, an example of photocatalysis, is responsible for the proliferation of eukaryotic life. However, 600 million years into the future, the opposite will be true, as the sun's higher luminosity means that circuit weathering will be accelerated to the point that most of the carbon dioxide in the atmosphere is returned to the rocks, effectively eradicating all eukaryotic life forms. With that, thanks for watching.